Good afternoon, or good evening, I should say. Well, I have to say that I'm excited to be here at this unique forum to talk about one of my favorite subjects, which is biomaterials. I'm a polymer engineer by training, and so what we do is we make materials to improve health outcomes for patients. So we do this for a variety of applications, cardiovascular applications, orthopedic applications, chronic wound dressings, but especially in terms of orthopedics, we're not only trying to help people live longer, but we want to help people live better, to restore that active lifestyle that's so critical. So I do biomaterial design, so we make new materials and we think about how do we construct them into these complex medical devices. Now, biomaterial design has been around for a little while. So back in the early Egyptian periods, we actually have evidence that they were doing prosthetics and they were doing dental surgery, which I would not want to have been this patient. Modern biomaterial science over the last less than 100 years has made extraordinary leaps and bounds in being able to restore function of whole organs, artificial organs, prostheses, regenerative medicine. And so my PhD research was in this area, and I was very interested, but it became somewhat of a personal story for me when I tore my ACL playing ultimate frisbee in graduate school. So just like that soccer player, that was me on the ground. And I think the ACL tear is that tear that you see when that football player goes down and everyone just cringes. It's tearing a ligament in your knee that's really required to provide lateral stabilization. And without that stabilization, you can develop osteoarthritis. This can be really a debilitating disease. So I was surprised, though, that when I went to my orthopedic surgeon, that they weren't going to use these new synthetic materials like the ones I was developing in graduate school. What they did, it was an autograft. So an autograft, if you're not familiar, is when I take tissue from a body and use it in the same patient to replace the damaged or missing material. So I'm creating an injury to treat an injury. And I can tell you, because my hamstring, which is where they took this graft to replace my ACL, has never really been the same. So I asked the doctor, why do we not have synthetic, why aren't you going to use the synthetic grafts that I know are available? There are synthetic ACL grafts. And he's like, well, if you want to come back in 2 or 3 years, I'll redo the surgery with another synthetic graft, and then we can do it again in another 2 or 3 years. And so functionally, creating an injury to treat an injury was giving better health outcomes overall than using synthetic materials. And that's because we still aren't able to match the complexity and function of these native tissues in a number of ways. And so that can be things like the meniscus is actually very difficult. This is the cushion between the bones in your knee. Is very difficult to match those properties. So it's amazing to me that we can send someone to the moon, and yet we cannot develop a material to match the properties of cartilage without failures in a relatively short time. So younger and younger patients are needing medical devices that can last longer. And it's not always that the material fails. So we can make, when you think about orthopedics, you think about those metal implants. Those metal implants aren't breaking. So when we have a hip implant that's titanium, it's not breaking, so we've solved that, it's super strong. But what's ending up happening is because it's so much stronger than bone, then the body thinks, well, that bone doesn't need to be there because it's not needed. The metal implant is taking all the load. So the bone density starts dropping and you get a fracture around the implant. Or if the implant doesn't integrate with the bone, if the bone doesn't grow in, then that implant can loosen over time and create problems as well. So it's not just the fact that we can't design something to match the properties, but if we don't match both the complexity and be able to integrate into the healing process, we get failures. And so if we look at why this is, again, what we were doing when we were first developing biomaterials is we were using the materials that had been developed for other purposes. And so we wanted for example, a doctor wanted a stretchy mesh that they could use for hernia repair, and so they looked at the pantyhose made out of polyurethane, and they used that material. And so we're using materials that are available, but not necessarily designed, and certainly they don't approach the complexity of native tissues. Native tissues, through countless evolutionary advances, have created this complex hierarchical structure. So if you look at the molecular level, it's organized. You look at the nanoscale, it's organized. You look at the microscale, it's organized. And we're trying to replace it with a homogeneous material. And that ends up with a mismatch. So what if we could do it a different way? And that brings us to biomimicry. The idea that instead of trying to figure this out on our own, let's figure out how nature did it and just copy that homework, right? So we're going to learn from nature in order to be able to design better materials and get better outcomes for our medical devices. So I would bet everyone's seen this biomimicry and used it. So Velcro was invented by a man who went on a walk with his dog. And when he came back, the dog had a bunch of burrs in his hair. And so when the guy looked at that, it was able to cling to the dog's hair really well. And so, but detach, reattach, detach, reattach. And so he went and looked at it closer and closer, and then took that microscale architecture and developed Velcro, and it becomes something that we use every day. So biomimicry is something that everyone in this room has used and is all around us in the world. We do great advances in technology by learning from nature. So the bullet trains were inspired by the shape of the kingfisher bird. And we look at how woodpeckers are able to absorb such amazing shock during their, woodpecking at the tree. Sorry about that. We can also design ventilation systems by understanding how termites build their mounds. And probably more biomedically focused, one of the unique things is shark skin is incredibly non-fouling, meaning nothing sticks to it. And so people are looking at how the architecture of the shark skin, as you can see here, can be replicated with nanofabrication to create things that bacteria doesn't stick to. So imagine I have a medical device now that I don't have to worry about infection. So we use this approach in our lab, and we think about biomimicry in two kind of distinct areas. One, we think about this idea that structure determines function. That if the body has developed a tissue or organ to have a certain structure, then that is how it's getting its complex function. And if we can mimic it, then we can get that function as well. The other idea is that cellular interactions are really driving healing. Cellular interactions are driving how the medical device is going to integrate with the body. And so if we think about synthetic materials cannot talk to cells. So if we can see what cell interactions are important and then copy those and put them into synthetic devices, we can create hybrid materials that are able to talk to our cells, talk to our body, and better integrate with that system. So I'm going to give you two quick examples for this. The first one being the idea of creating the complex structure of a tissue and being able to get greater function because we did that. So if you look at bone, generally think bone, relatively straightforward, but bone is actually a very complex tissue. So you have this spongy inner core that's been reinforced by this really dense, strong cortical shell. And then throughout it, you have these canals that allow your blood vessels to go in and provide the nutrients to allow the bone remodeling. So what we wanted to do was mimic that structure. And so we do that with something we call multi-material 3D printing. And in this case, we use one printer to print the porous inner matrix, okay, that allows for good cells to come in and integrate. And then we print another one that allows us to get that cortical shell. And since we're 3D printing, we can create that complex channel structure to allow for blood vessels to grow in. So we think a lot in terms of manufacturing and how this is going to make sense as a medical product. So I just told you about pretty advanced additive manufacturing. And I'm going to have to demonstrate that there's going to be a good clinical benefit to pay for that additional cost and time in terms of manufacturing. So what do I get by getting this complex function? Why do I need it rather than just having something that I can make much more easily? And the challenge here is that we have property trade-offs in any kind of medical device. Nothing is free, okay? So if I want something that cells are going to be able to grow in, that bone's going to be able to grow in, generally I make it porous. I make holes for the bone to grow in and lock in that substrate. But if I make it porous, I'm taking material away, it's not going to be as strong. So what I get by having this design, again mimicking bone, is I get something that's able to let cells grow in, but it also still retains that strength. And so that's what I get by having these more complex. Again, what we're doing is we're creating more hierarchical organization in order to balance the trade-offs in these designs. So the other example I want to give you is how we can learn from cellular interactions to create, again, synthetic materials that can talk to cells. And so for this one, we used collagen as our design base because collagen is part of every tissue, practically every tissue in your body. So it does a little bit of everything. And so we can use that to create different products that can talk to cells. So cells are used to interacting with it. Great. The problem is that we can't make collagen in the lab well. So we can make the other proteins like insulin in the lab well, but we can't make collagen for a number of reasons. The other problem is because collagen does all of these different things, then there's no way for me to optimize it, say, to enhance bone regeneration, right? So it's in bone and skin, and it has to be able to do both bone and skin. How do I make it so it does something specific in bone? So I work with a company called ECM Technology. So as a disclosure, I am a stakeholder in this company that seeks to commercialize these designer collagens. And what they're making are specialized collagens that we can synthetically make in the lab and scale up like insulin was scaled up, but that we can also optimize for a specific regenerative purpose. And so in this case, the analogy is this, like collagen is a one-man band. Okay, so it can do a little bit of drums, it can do a little bit of guitar, but if you just put it in, it's going to just make a cacophony, and your cells are going to hear a lot of different messages that may or may not help you regenerate whatever tissue you're trying to target. With our designer collagen, we get one signal that we can optimize for a specific purpose. And so by having engineered cell interactions, we're able to better optimized for different regenerative processes, whether or not that's in cardiovascular applications or orthopedic applications. But we don't just have to take our inspiration from the body when we're making medical devices. We can also look outside of the body in other areas of nature. And so when we wanted to make a tissue sealant that's going to be able to adhere to pieces of tissue underwater, we looked at aquatic mussels. So aquatic mussels are really good at sticking themselves pretty much anywhere if you do any boating. So what we did was we took the same chemistry that these aquatic mussels use to have such great adhesion underwater and use it to do a variety of different applications. So in one case, what we do is we create this adhesive bone wrap. So you might think of it as a bone Band-Aid that works underwater, where we put this on, say, a fracture from a battlefield injury, which has a high probability of being contaminated. And that wrap is able to both boost regeneration as well as fight the infection by releasing antimicrobials. We also use this to basically go around anytime we do an abdominal surgery, like a colon resection, to prevent the adhesions that can cause complications. So the last thing I want to highlight here is when I talk about biomimicry, I mean inspiration and not emulation. So this is Leonardo da Vinci looking at how to learn how to fly. We are not flying. Did anyone come in on this structure here? No one wants to do that? So we can learn from it, but we're not necessarily going to fully mimic the tissue. I just spent all this time telling you how awesome the tissue is. Why wouldn't we want to fully mimic it? Because it's really hard. So this has happened over countless evolutionary changes, and we would spend an inordinate amount of engineering time and effort to be able to fully replicate it. And as an engineer, it may not be necessary. So what we do is we look at why is this medical device failing now? Why? And then we look at that, figure out how the body fixes that part, and then use that in our design. So it's a targeted, strategic biomimicry rather than full replication of a tissue structure. And so we're going to identify that target. We're going to use our technology to be able to mimic it and put it into our design with the idea of being able to improve clinical outcomes. So I hope that I've given you a snapshot or a quick glance into biomimicry and how it can be used to design better biomaterials. With that, I'd like to acknowledge our funding sources. NSF and NIH have funded our lab for the last 10+ years, our collaborators, and of course, the amazing students that I get to work with every day. So these are a number of my graduate students and undergraduates are in the lab, and I would really like to encourage you to come visit us at UT Austin, visit us online, or feel free to email me. Thank you very much.